So now we're going to convolve a rectangle with a rectangle. This rectangle is half a second wide and goes to 1. This is a quarter second wide and goes up to 4. And we can just expand these to where we get step convolved with step, minus step convolved with a delayed step, minus step convolved with a different delayed step. And then 2 steps convolved with each other, and they both have delays. Well, step convolved with step is ramp. All we have to do is scale and delay, so scale by minus 1, plus, then multiply through by 4, and then just sum the delays. So minus quarter second, half second, and 3/4 of a second. And so now we know there's some time before t equals 0, where it's 0. Then we have a positive slope, then the slopes cancel. Then we have a negative slope, and then the slopes cancel. Right? And this can be seen here with these plots. Now understand, in these plots the axis is tau, right? And where the rectangle is depending on your value of t. So in this case, t is well below 0, so there's no overlap. And that's where we are. And if this were to move, right, it'd be 0 until it started to overlap. And now in this region, between 0 and a quarter, that overlap is increasing linearly. Well, that's what we're integrating. Right? So that has a slope of 4, right? And it stops at a quarter, so we go up to 1. Now we have this region where the area isn't changing, right? So it's flat. Then as the rectangle starts to leave, it's the overlapping area is decreasing linearly, and then there's nothing left. It's just 0. So let's go to our animation. And I have noticed a mistake. I should have called this tau, right? Because if I were to freeze frame it, this position is controlled by advancing t, but the plot of tau, right, it's all there. It's not moving, if you will. The only reason why this is moving is because I'm stepping t forward. So let's just let it come around again. Right, it's coming in. There's nothing to integrate because there's no overlap. Right, and when t moves this rectangle to where it's here, we see that area increasing linearly, but then there's no increase in area, and then it's decreasing linearly until there's no area to integrate. Okay? And so sometimes there's things you can remember, that if both shapes start and end at 0, your final convolution will start and end at 0. Right? And the thing is instead of a rectangle here, we could have an exponential decay representing a low-pass filter. And we would get the step response of a low-pass filter. Sure, instead of a straight line, this would be that exponential approach, and this would look like exponential delay, but they both start and end at 0.